All right. So welcome to our Form 5 free seminar. Okay. So this is supposed to be your seminar for your first term exam. Have you all had your first term exam ready? Probably not, right? Otherwise, hey, you got ready. I already had your first term exam. Okay, if your first term exam was that early, right? Because some schools I know haven't have their first term exam yet. But if your first term exam is that early, that means you're gonna have a midterm exam also. Okay, so what we're gonna learn here will be for your midterm lah, if you had your first term exam ready. Yeah, okay. All right, so in today's seminar, we will focus on force and motion. Part 2. I mean, doesn't really matter part 2 or part 1, but just force and motion, because we're going to be combining it with the Form 4 force and motion also. Okay, so here we have a checkbox, and this checkbox is just for you to find out whether you're prepared or not. Okay, like, do you already know the definition of this? Do you already know the effect of this? Do you already know how to do the free body diagram? So on and so forth. Okay, you can see here most of it is just on forces and one small part on elasticity. Okay, so I will not focus too much on elasticity today lah, right? You can see that there are a total of 6 questions that we'll try to do today. Okay, just now in the Mandarin class, I managed to do 5 of them, and only one of it was elasticity. Okay, so I predict that it'll be the same for us as well lah. Okay, I should only have time to do 5 of it only. All right, so the last one is one of the spring question. I'll just skip it. Okay, all right, let's start off with a very quick recap. Now, when it talked about forces, okay, of course, you cannot escape from the equation F is equals to ma. Okay, force is equals to mass times acceleration. This is actually Newton's second law. Okay, now Newton's second law, the F, right, is not just force only. The F here stands for resultant force. Okay, resultant force or net force. And just in case you don't remember what is resultant force or net force, right? It's basically when you have a box, let's say an object, and you have forces all around it. Okay? When you try to combine all the forces into just one force, that is the resultant force. Okay? So opposite direction, you minus off, same direction, you add to each other. Okay? So basically, resultant force is one force to represent everything. Now, if that resultant force is 0, that means that the forces are balanced, or we say that the thing is in equilibrium. So if they ask you, what's the meaning of equilibrium? You tell them, there's no resultant force. Okay? The resultant forces are 0. So like anything on the left side is equals to the right side. Anything going up is equals to going down. So that's why they cancel each other out. Okay? So that's why the forces are 0. And if the forces are 0, the acceleration must be 0. Because that's the only way you can get 0 here. It's 0 times something equals to 0. So acceleration is 0. Okay? Which means this thing is not accelerating. There are 3 possible explanations that this thing is not accelerating. I'm sorry, 2 possible explanations when we say this thing is not accelerating. It's either the thing is not moving at rest, or the thing is moving, but it must maintain the same velocity. It must maintain the same speed. Okay? And same direction. Basically traveling with constant velocity. Yeah. So for those that come to my class, you know the example that I always give lah, which is that let's say you are in space and then you got pushed in space. You will start to float ma. And when you start to float in space, right? Nobody's pushing you, nobody's pulling you. The force on you is 0, but yet you are still moving because you are moving at constant velocity. Okay? So that is when there's no resultant force on you. All right? Okay, but if the resultant forces is not 0, if the forces are not balanced, right bigger than left, up bigger than down, there is a resultant force. If there is a resultant force, there must be an acceleration. Okay, yeah. So we're saying that there is an acceleration, got acceleration. Now, got acceleration means one of three things. Okay, you speed up, you slow down. Okay, you slow down, or you change direction. Don't forget, changing direction also means accelerating. Okay, because velocity got direction, right? Yeah, so that is when your force is not zero. You have an acceleration. So there is a resultant force. Okay, just something to keep in mind. Okay, now, if they give you the forces and you want to calculate the resultant forces, it's pretty simple. Okay, if let's say it is like this, 90 degrees, the force they give you is 90 degrees, like that and like that. Okay, yeah, like that and like that, 90 degrees. All you have to do is just get the Pythagoras theorem. Okay, Pythagoras theorem, 1 square, this square plus this square is equals to the resultant square, then you get your resultant force. Okay, that's a normal calculation. But let's say if it's not 90 degrees, then you might need to use a drawing method. Your exam might ask you to draw, it's a possible thing. Okay, so when they ask you to draw a scale drawing, you need to first determine what's a scale. For example, 1 Newton, you will draw it as 1 cm. So 5 Newtons, you draw at 5 cm. Okay, or maybe 10 Newtons is equals to 1 cm. So 100 Newton, you would draw it as 10 centimeters. Okay, you decide the scale. Then you have two things. Either you do a triangle method or a parallelogram method. At the end of the day, they are the same. Just, I don't know why they got so much pattern only. Okay, I don't know why they need to have two different patterns even though they're doing the same thing, right? Okay, first of all, these are the two forces given to you. F1, F2. Okay, they ask you to find what is the resultant force, FR. Okay, so if you want to do the triangle method, the way to do it is you draw one first, okay, then you take it and you put it right after the other one. Okay, you draw one after the other. So one first, and then the other one continue from there. Okay, and then you go start to end. Start to end. That's the resultant force. Okay, now it doesn't matter which one you want to draw first. You could always just draw the F2 first. Okay, let's say like that. You draw F2 first. Then only you take the F1 and you connect it after it, one after the other. Okay, then you draw start to end. That's your resultant force. Correct? Okay, now if let's say they purposely ask you to do parallelogram method. Okay, parallelogram method is like this. This is F1 correct? You take the F2, you draw it right after the F1. Isn't it the triangle method? Isn't that what we just did in the triangle method? Then you take the F1 and you put it right after the F2. Isn't that the triangle method? Didn't we just do that? Correct? It's the same thing. It's the exact same thing. Okay, just that now you have to do it both together. And then again, same, from start to end. Okay, from start to end. That's your resultant force. Okay, now, yeah. So this is how you do the resultant force using the drawing method, scale drawing method. Okay. All right. Oh yeah. By the way, after you get this, you have to measure you measure what is the length of this. So if let's say this is 6 centimeters, then you can see 6 centimeters is equal to 6 newtons or 6 centimeters equals to 60 newtons depending on your own scale Okay, so you just measure what is the length. Yeah. All right, now, we have just taken two forces and combined them into one, right? So resolution of forces is the reverse of that. Okay, you get resultant force, right? It's combining two into one. Resolution of forces is the reverse. We take one force and we split it into two different forces. Okay, yeah? One force that is sanged can always be split into two, a horizontal and a vertical. Okay, and it's very simple. This is a force going to the top right corner. Okay, this force is pointing to top right. So it can be split into top and right. Okay, this force can be split into top and right because it's going to the top right corner. Right? If let's say this force, this is going to the bottom right corner. Okay, so if this is going to the bottom right, it can be split into bottom and right. Okay, so you just need to figure out where is this pointing towards. You split into top or bottom, right or left. That's it. Okay, so then you will be able to get the horizontal and the vertical. Okay, horizontal usually we will call it X lah, and then vertical we call it Y lah. So for example, let's say this force is called A. Then we will call this AX and AY. Okay, if this force is called let's say this one is called J, then we will call this horizontal one JX and JY. Okay, yeah. So how do you find how much is this? If let's say they've given you this and they've given you the angle, let's say any angle, right? So what you need is your so, ka, and tua. Actually, mostly just your so and your ka. Okay? Now, please remember, the so and ka actually means what? Actually means sine theta and cos theta. Okay? Sine of the angle is opposite over hypotenuse. Cos of the angle is adjacent over hypotenuse. So if let's say I use the so, I use the sine, I can say that sine angle, whatever lah, let's say this is 30 degrees, so sine 30 degrees or whatever, okay, sine angle is equals to, who is the opposite from that angle? So the angle is here, his opposite is JY. Okay, divided by, hypotenuse is always that longest line. Hypotenuse is just that line that is opposite the 90 degrees. Okay, that's a hypotenuse. So it's always the J or the F or the A. Okay, yeah, it's always the force. So then if I want to find out what is JY, I could just say JY is the J sine angle. Okay, yeah, if all of this is F, then this will be Fy equals to F sine the angle. Okay, so that's how we get this one. Okay, now you see there's a problem here, correct or not? The problem is that his is cos and ours y, right, is sine. So that's why I don't want you to go and memorize this thing. I want you to be able to do it yourself. Find out yourself what is the relationship, sine or cos. Okay, because if you memorize this, once they change the direction, they change the angle, you are dead. Okay, understand? Yeah, so make sure you follow this one. Manually do, don't go and memorize. Okay, all right, so if you want to get fx, you just do the same with the cos. Then that would be fine. Okay, you get it. All right, now inclined plane is actually the same idea. Okay, It's just that instead of splitting into horizontal and vertical, you split into parallel and perpendicular. Listen later after we finish everything, only I brief this again. Okay, because there's no question here about inclined plane. So after we finish, then only I will briefly go through this again. Okay, remind me if I forget about the inclined plane. Okay, if you have things that are in equilibrium, meaning all the forces are balanced with each other, okay, then you can solve a question like this easily. Because you see, this one, right, you just need to take this Saget force, this Saget force that's going where? Going to the top left corner. I just need to change this force to a top left force. Okay, I just need to change it to a top left, right? Doesn't matter whether you draw it here or you draw it the other way, I don't care, as long as there's a top and there's a left. Okay, then you get what is the cos and sine for these two. Okay, so instead of calling it horizontal and vertical, instead of calling it x and y, I want it to be like T1 sine 50. This is T1 cos 50, like that. Okay, yeah. So I want it in that version. So now you split into these two, right? This one doesn't exist anymore. Okay, this doesn't exist anymore. So then you can say up is equals to down. Left is equals to right. Okay, so then you will be able to solve T1 and T2 easily. Okay, you'll be able to solve it. Yeah. All right. Any questions? Any questions? Up to here. Okay, no problem. Okay, this one is just the same. I'm not gonna talk about this because it's just exactly this only. Okay, you just stick with what I've just told you. Okay. All right. So if there are no questions, then let's start to do some exercise. Elasticity, maybe later before we do the spring, then only I'll talk to you about it. Okay. So let's go into some exercise first. All right. Question number 1, page number 7. Yeah. Diagram 6.1 and diagram 6.2 shows a lawnmower move with 2 different methods. The force acting on the handle F can be resolved, meaning the F, the force can be split into vertical component Fy and horizontal component Fx. Okay. Define the resolution of forces. So just how I say what? Resolution of forces means I take my F, resolve into Fy component, vertical component, and horizontal component Fx. Right now, it's literally here in the question already. Okay, so you say resolution of forces is the process of resolving. They use the word resolve, resolving one force into one component into 2 components. Okay, resolving one force into 2 components. Yeah, isn't that what they are saying here in this line of the question? Resolve the F into Fy and Fx. Resolve one force into 2 components. Okay, next, draw the diagrams of a triangle to show the resolution of forces. Show how you are splitting the force. Okay, for 6.1, where is the force? The force is this, push. Okay, let me use a thicker line. Okay, this is the force, push. Okay, where is this force pointing to? This force is pointing towards where? To the bottom right corner. Correct or not? The force is pointing to the bottom right corner. So it can split into bottom right. Okay? Yeah? This force can split into bottom right because it's going to the bottom right corner. Correct or not? Okay. Now, the other one is a pull. Pull where? Pull which direction? Pull this direction. Okay, pull this direction. This is pointing towards where? This is pointing towards the top right corner ma. Okay, so top right corner means I can put it as a top and a right. Okay, I can put it as a top and a right. Now, of course, it doesn't matter whether you draw like that. Okay, it's correct also. Yeah, it doesn't matter if you draw this like this. It's correct also. As long as the component is correct, as long as this one got one bottom and one right, this one got one top and one right. Okay, so one right and one top also can, same. Yeah, so horizontal one, we will call them as fx. That's what the question says. Vertical one, we will call them as fy, also written in the question. Okay, now listen. And any questions, you just ask me. Okay, straight away, no need to be shy. Okay, so based on diagram 6.1 and 6.2, compare the method of moving the lawnmower. Okay, compare questions. Most of the time, use your eyes only. Okay, yeah, just once in a while, maybe you need to use your brains, but most of the time, use your eyes. Use your eyes to see what's the method of moving the lawnmower, 6.1 and 6.2. The method of moving, this is push. The method of moving, this is pull. Okay, so you say method of moving is push in 6.1 and pull in 6.2. Correct? Yeah, method of moving is push in 6.1 and pull in 6.2. Okay. Now, compare the direction of force, not the F, the force in the vertical component. Compare the direction of Fy. Again, your eyes can tell the difference or not. The direction of Fy. This one Fy, going down. This one Fy, going up. Okay, so we say direction of Fy is downwards in 6.1 and upwards in 6.2. Okay, direction of Fy is downwards in 6.1 and upwards in 6.2. Yeah, all right, then compare the net force acting upon the ground surface. Okay, this one need to use your brain a bit. Yeah, this one need to think a little bit. So what is the force acting upon the ground, meaning the force on the ground? What is the force towards the ground? Okay, so if you push down, surely you will have more force towards the ground. This is not towards the ground, correct or not? So you can say the net force upon the ground in 6.1 is greater than in 6.2. Okay, the net force upon the ground in 6.1 is greater than in 6.2. Okay, Now, after all compare questions, the next question will always be relate. Okay, this is a fixed pattern already. Once you finish compare, you have to relate. So what are they asking us to relate? Relate the direction of force in the vertical component. So relate the direction of Fy and relate the net force acting upon the ground. So relating number 2 and number 3. Okay, so it's up to you whether you want to talk about 6.1 or you want to talk about 6.2. If you say 6.1, then you say direction downwards, net force greater. Okay? If you want to talk about 6.2, then you say direction upwards, net force smaller. Okay? Yeah? It's just like that, right? Based on your own observation. So let's say I talk about 6.1. Okay? Then I'll say, since because 6.1, the direction is downwards and 6.1, the net force is greater, I can say that when the direction of Fy is downwards, okay? When the direction of Fy is downwards, the net force upon the ground is greater. That's it. Okay, just follow your observation. When the direction of Fy is downwards, the net force upon the ground is greater. Okay, so they ask you, which method is more suitable to cut the grass more efficiently, and give reason for your answer. Now, if you want to cut the grass, you want the lawnmower to be as close down to the ground as possible. You want the lawnmower to be as close down to the grass as possible. So we need to choose the one that will press the lawnmower down, okay? Which is the pushing method. Yeah, we need to choose the pushing method. Okay? Yeah, it is more suitable because the downward force is bigger. The downward force is bigger, and you can say the lawnmower is pressed towards the grass. Okay, pushing method, because the downward force is bigger and that makes the lawnmower press towards the grass. Get it? Okay, so now we have a wheelbarrow. Okay, we have a wheelbarrow. And the wheelbarrow, right? You need to choose which method to move the wheelbarrow is better. We have a push and a pull method. Okay, just push and pull only. Now, most of the time, right, you see people use the wheelbarrow, they push one, right? Okay, but if you think about it, when you push, they are not actually pushing down like this one. They're actually lifting it up and then only pushing it forward. Okay, so when they talk about push here, they mean push down like that. Okay, in this question, they mean push down like that. And actually, we don't push it down like that one. If you want to push, right, you have to push this way. Okay, so that is the correct push. But here, in this question, their push actually means like that. Okay, which is actually not helpful for the wheelbarrow. Because even though for the lawnmower, right, we want to press it down to the ground. For the wheelbarrow, actually, no ma. The weight is going down. We actually want to push back up ma. Correct not? To carry the wheelbarrow. So actually, for wheelbarrow, we will rather it to be pull in this direction. Because this way, you are moving forward, yet you are also lifting up. Okay, you're also lifting up, right? So, method to move the wheelbarrow, we're going to go with pull. Okay, we're going to go with pull. Now, the reason, because the vertical component, which is the Fy, is upwards. Okay, so the net force decreases, right now. Because if the weight already is pushing down already, then somehow you push down lagi, then you will make the net force even bigger only ma. Right? Yeah. Okay. All right. So next one, the size of the tire. Okay. So the size of the tire has to be a big tire. Now, why a big tire? Because we learned that when you have a bigger tire, you have a bigger surface area. What happens to the pressure? The bigger the area, right? The smaller the pressure. Okay? Smaller the pressure. So this will cause it to not sink into the mud. Because construction site, there's a lot of mud. Okay? So we don't want it to sink down. So that's why we need the tire to be bigger. Okay? Nothing to do whether with heavy or not. So we want bigger tire. Okay? Bigger tire so that bigger surface area. Okay, bigger surface area, smaller pressure. Okay, so our choice here is gonna be L, right? Because it also has a big tire. So wheelbarrow L. Okay, wheelbarrow L. Okay, besides all these characteristics, what is another characteristic? Can you let me know what other characteristics of the material should I use? Like what kind of material should I use to make the wheelbarrow? Any ideas? Besides all this, besides the method and the tire, what kind of material should I use for the wheelbarrow? Any ideas? Okay, you make it lighter. Okay, now to make it lighter, right? What kind of material do we use? We don't say light material. We will say use low density material. Okay, use low density material so that the wheelbarrow becomes lighter. Okay, then basically you can carry more stuff lah. All right. Now, if you want it to be more durable, then you have to say use a strong material. Okay, you can say use a strong material so that the wheelbarrow is more durable. Okay, you have to say that the wheelbarrow is lighter, the wheelbarrow is more durable. Okay, this is your reasoning. All right. You don't mention the name of the material. For all these kind of essay question, right? Never mention the material. Okay, because if you give a wrong material, it's straight away wrong. So we give the characteristics, correct? Okay, so unless the choices inside, right, already told you, let's say this is steel, iron, then you have to decide iron or steel. That only in that case you can write the name of the material. But other than that, you just write the characteristics. Okay. All right, next, let's look at this triangle hanging question. Okay, so this hanging question, there are a few kinds. One kind is hanging like this, one kind is hanging like this, but the idea is the same one. Okay, it's the same idea. Let's see. Archaeologist, mass 65 kg, stopped to a rest in the middle of the rope. Okay, he stopped here. What is meant by force in equilibrium? Just like I mentioned already, what do we say when they ask you what's the meaning of equilibrium? You say that there is no net force or no resultant forces. Either one, both mean the same thing. There are no net forces or there are no resultant forces acting on the object. Okay? No net force acting on the object. All right. Can an object still move when in equilibrium? Yes, can. Okay, that's why we say even when the force is 0, you can still be moving, but you can only move with constant velocity. Cannot accelerate, cannot decelerate, cannot change direction. Constant velocity only. Okay, so draw the triangle of forces for the weight and the tension of the rope caused by the archaeologists. Okay, this question is considered very good already, because they tell you, right, that your triangle need to have weight and the tensions. Okay, tensions, right? So some questions they don't tell you one. They just say draw the triangle of forces. Then many students will do what? They just draw this. Wrong. Okay, many students will just draw this only because that's the triangle they see. But no, you have to draw the triangle of forces. Okay, now these ropes, these strings here, there is a force inside. There is a force here pulling this guy up. That's the tension. There is a force here pulling this guy up. There's a tension. And then many students cannot find where's the third force, because the third force is the weight. Don't ever forget that weight is a force. Okay, please, you have to remember this. Weight is a force. So there will always be this force on our body forever. Okay, all right, so you have to draw a triangle with these 3 lines. Okay, if you cannot see how it moves, right, what you need to do is you need to take 3 pens and put the pens pointing according to this. Okay, 1 pen here, 1 pen here, 1 pen here. Okay, then you have to move the pen around until you get a triangle. I don't care how, but move it around until you get a triangle. Let's say like this. Okay, yeah, that is one way to make the triangle. Another way would be like this, also a triangle. Yeah, it's up to you. But remember, you can only move the pen. You cannot rotate the pen. Okay, so this will be your triangle of forces with the weight and the tensions. 2 tension. Okay, now. All right, now of course it will be better if you can add in the angle as well. So the angle, right, will actually be here. Let me wait. The angle actually is going to be here and here. Okay, this is theta, this is theta. Yeah, Don't go and put it here. You can see this shape is definitely not the same as any of this shape. Right? Okay, this is not the same angle. All right. So actually here and here. Okay, so then you have to calculate the tension, calculate the T, if both the angles are 20 degrees. Okay, now whenever you have a hanging question, what I want you to do, right, is to find one of the T. Okay, and to find one of the T, right, you need to use half of the triangle. Correct or not? 2T give you the whole triangle, but I only want you to use half of the triangle only. Okay, so half of the triangle will look something like this. Right? This is T. And what is this here on the right? This is not W anymore. You have just split the W in half. So this is W in half. Yeah. Okay. It's half of W. It's up to you whether you want to calculate this first or calculate this later. It's up to you. You could always just calculate what is half of W first. So long as you remember, W is equals to mg. Okay. So W over 2 is just mg over 2. Right? Then you can calculate how much is this. Okay. Mg over 2. The mass has been given to you, 65. The G, as always, 9.81. Okay? The angle is here. One of the angle, that's 20 degrees given in the question. Okay? So, all right. So then you have to take out your SOHCAHTOA again. Okay? So you can try and error, right? If let's say you try to use car and you realize, hey, there's no adjacent, then it's not car, so it's actually sine. So sine 20 is equals to opposite over hypotenuse. So the opposite of the 20 is this guy. This guy is the W over 2. If you've calculated how much is it already, you can just put it in there. Okay, otherwise you just leave it as W over 2. And then over hypotenuse, which is the T. Okay, so you bring this up, become multiply. T sine 20 equals to W over 2. Okay, and then you bring the sine 20 over, divide again. So T is equals to half of W divided by sine 20. Okay, can you get me what is this? You find out what is a half of W using mg over 2, then you put this over here. Okay, then divide it by sine 20. Wow, so fast. 932.18. The rest of you got 932.18 or not? What is a W over 2? What is the half of the weight? 653 something, 300 something. Okay, if you get your W over 2 is 318.825, then you should get this T also. Okay, if you can get the W over 2, 318.825. Okay, now tension is a force, newtons. Okay or not? The rest? Okay or not? Right, so that is how you calculate the tension of this kind of question. Okay, so just split it in half. They just ask you to calculate one tension anyway. I mean, both will be the same anyway. It's going to be 932 here, 932 here. Okay, both are going to be the same. But you just need to calculate one. Okay, so another method of hanging something, right, will be this way, the hanging photo way. Okay, And later on, you see, right, what we do is going to be the same. Okay, so here's a painting. The weight of the painting is 15 newtons. Here, W, 15 newtons. Okay, going down. Each string can withstand a maximum force of 10 newtons. This one can withstand 10, this one can withstand 10. What is the meaning of weight? Okay, weight is what? Remember, weight is a force. Okay, so the force of what leh? Weight. I'm just going to write this first because I want you to remember this. Weight is a force. It is actually the force of gravity. Okay, it is a force of gravity on an object. How strong is the gravity pulling on that object? Okay, now, a few seconds after the painting is hung, it is found that the string of the painting snapped. By using the value of the angle theta equals to 30 degrees, calculate the tension of the string and the resultant force. Explain why the string of the painting snaps. So again, you see, there are two tensions here. 1, 2. Okay? It's always like that. It's always two of them, tension. Okay? So we're going to do half of the triangle again. We're not going to do both of the T, just one of the T only. Okay? So we're going to do half of the triangle again. So half of the triangle, I'm going to go for this. Right? So this one is going to be like that. T. Okay? This one down. And then horizontal doesn't exist. Okay? The down again, I split my weight into half, because one side only take half the weight, the other side in charge of the other half. They share one ma. So this is gonna also be W over 2. Okay? All right. Same thing, angle 30 degrees. Okay, 30 degrees. So let's have a look. Sine 30 degrees equals to opposite over hypotenuse. Opposite of the angle is again W over 2 over hypotenuse is again the tension T. So T is equals to, again, I bring up here, become multiply ma, right? Multiply, so it's like T sine 30 equals to W over 2 is 15 divided by 2. This one no need to convert already. Okay, this is 7.5 already. Okay, so T is equals to 7.5 divided by sine 30, which is what? 15. This is 15 newtons. Okay, you should be able to calculate that the tension is 15 newtons. 15. Okay. All right. Next, the painting is broken when it drops from a height of 4 meters. By ignoring the air resistance, calculate the time taken for the painting to reach the floor. Okay, so there's a distance, there's a time taken. This smells like what? This looks like what? This tastes like what? This tastes like a Suvat question. This smells like a Suvat question. Then there's a distance, there's a time, okay? So this is a Suvat question. Okay, so we'll start with the S. How far is it going to travel? It's going to fall for 4 meters. Okay, the initial velocity of the painting when the painting first dropped, before it dropped, it was hanging. So it was 0 meters per second. That is right before it dropped. Okay. Now the final velocity after it dropped for the whole 4 meters, right before it reached the ground, what is the final velocity? We actually don't know. That's actually the next question. Okay. For the A, the acceleration, now this thing is falling down because of what? It's falling down because of gravity. So your acceleration is going to be 9.81 ms negative 2. Okay. The time is what we're trying to find, the time taken for the painting to reach the floor. So we don't know. Okay. So in this first question, right, we have S, U, A, and we're trying to find T. So I need a Suvat equation with S, U, A, and T. It is S equals to UT plus half AT squared. Okay, yeah. And then the velocity one, again, I have S, U, A, and I'm trying to find V. So we need an equation with V, U, A, and S. So that's going to be V squared equals to U squared plus 2AS. Okay? So I want you to substitute all the numbers inside and then get me what is T and what is V. Okay? Remember to square root it up. Okay, what is T and what is V? Let me know if you are stuck anywhere. Okay? Let me know if there are any problems while you're calculating. Kenna, what do you get for T and V? Oh, can find out. Any problems finding or not? Just substitute the numbers inside. Okay, so T you get what? T you get 0.903. Okay. Time is in what? Time is in seconds. Okay, time is in seconds. Yeah, and then the V, the velocity, final velocity, you get 8.86. Okay, you get 8.86. Velocity is a meter per second, right? ms-1. Okay, so that is velocity. Okay, the final velocity. Now, state one reason why the painting is broken. Why when the painting lands on the floor, right, it will break. Okay, it's because this is actually the answer. They forgot to remove the answer here. Yeah, so this is basically the answer. Because the time of impact is very short when the painting lands. Okay, so remember we learned something called impulsive force, which is where F equals to mv minus mu over t. So if this impact time is very short, you get a very big impulsive force. That's why it breaks. Okay, the time of impact is short when the painting lands. Therefore, the impulsive force acting on the painting is huge. Okay, or the impulsive force on the painting is very large. Okay, that's the reason why. Can I? Okay, let's look at this question here, the next question, question E. So the table here shows 4 methods to pull a lorry that is stuck in mud, okay, by 2 other smaller 4-wheel drive vehicles. Okay, so we need to decide which is better angle, which is a better type of cable, better maximum tension, and any supported material below the tire. So first is the angle, okay? Now, of course, you can do some calculation to figure out whether 30 degrees got more force horizontally or 60 degrees got more force horizontally. Okay, but okay, the drawing here actually is not correct lah. It's not supposed to draw like that. Okay, but I'm just gonna show you based on drawing. You see, the goal here is to get the most amount of horizontal pulling force. Correct or not? That's what I want. The most amount of horizontal pulling force. Okay, if let's say your forces are like this, 30 degrees, this is 30 degrees, okay? Then if you think about this one can be split into horizontal and vertical like that, correct or not? Yeah, this one can be split into horizontal and vertical. This one can be split into horizontal and vertical like that. Okay, so you see when it is at a 30-degree angle, your horizontal focus is much more than your vertical. You are spending more of your force on the horizontal than on the vertical. But if let's say you are 60 degrees like that, okay, this might be more than 60 degrees but I'm just showing you an example only. Okay, if a bigger angle. Now with a bigger angle, right, you are actually transferring more of your force to the vertical. Can you see that or not? Yeah, can you see this happening or not? You are transferring more of your force to the vertical instead of having your focus on the horizontal. Okay, so like that, not good for this situation because right now I'm trying to pull the lorry out. So I need more of your focus to be on the horizontal, not on the vertical. Okay, so I need the angle here to be small as possible. Okay, so I want a small angle. Small angle between the cables. Why? So that my horizontal component is greater. Okay, greater horizontal component. Okay, greater horizontal component or greater pulling force. Yeah, because this is the force that's pulling ma. This one you're just pulling each other only. You're not really pulling the lorry. Okay, only this is pulling the lorry. All right, next, the type of cable. Now we have a cable that is elastic or inelastic. Okay, now have you ever tried pulling something with a rubber band or not? Yeah, you will know if you've ever tried pulling something with a rubber band, that when you try to pull, the thing won't move on because the rubber band was stretched. Then only suddenly the thing will move in front. Okay, so that's not good. Yeah, when I pull, I want my force to transfer to the lorry, not waste my force to stretch the string, stretch the cable. Okay, so I'm going to choose an inelastic cable. Inelastic cable, so that it does not stretch. Okay, does not stretch when pulled. Right? It does not stretch when pulled. Okay, then the third thing, the maximum tension of the cable. Maximum tension means how much can the cable handle, right? How much pulling force can the cable handle before it snaps? So of course, we're going to choose the one with the high versus the one with the low, right? Not, yeah, we choose the one with the high pulling, high maximum tension. High maximum tension so that it does not snap easily. Okay, or you can say does not break easily lah, same thing lah, right? Does not snap easily, does not break easily. Okay, and finally the supported material. So you can have a choice either to not put anything under the tire of the lorry, or you can put a papan kayu, which is not elastic cable. A papan kayu is a wooden plank. Okay, he wrote wrongly already. So I want a wooden plank at the bottom. Why? Because the reason why the lorry fell into the mud is because the pressure is too high already. It pressed into the mud and it just sinks into the mud. So what I need now is to reduce the pressure by increasing the surface area. Right now, so it's a wooden plank under the tire. The reason is to increase surface area, or you can say reduce pressure also can. Okay, so small angle, high tension, wooden block, inelastic. Our choice here will be method S. Method S is most suitable because yada yada yada. It has a small angle, it has inelastic cable, it has high maximum tension, and it has a wooden plank. Okay, Ken? All right, 3-minute break. Okay, we'll meet back here at 5:11. Okay, not too long, 3 minutes only, right? Just for you, enough to pee and drink your water. Okay, so I'll meet you again at 5:11. Don't be late, Okay, and we're back. Right. Now, the next question is about the spring. So I will briefly talk about the spring first. Okay, the elasticity first, and then we will go to that question. All right, for spring, there's not much you need to remember. First of all, it's just Hooke's law. Hooke's law says that F is equals to Kx. The force is equals to the spring constant times the extension or compression. What is this spring constant? It means stiffness. How stiff is the spring? That's the meaning of the spring constant. Okay, the higher the number, the more stiff it is. So if you have a graph of F against X, force against extension, you will see the graph being directly proportional. because that is what Hooke's law says when he said F equals to Kx. He said that force and extension are directly proportional. That's why you get this straight line starting from 0. But at some point, it will stop being directly proportional. It will stop obeying Hooke's law. That is when you've gone past the elastic limit, which means you made the thing not elastic anymore. The thing cannot go back to the original shape and size anymore, okay? You have basically broken the thing, right? Okay, from this graph also, you can get the gradient, which is F over X, but just so happen F over X is the K. So the gradient is the spring constant. The more the gradient, the stiffer the spring. The flatter the gradient, the smaller the gradient, the less stiff the spring is, okay? And then there is this thing called elastic energy, which is the energy stored inside the thing. Let's say it's a spring, and I press it, the spring has energy stored inside it, elastic energy. When I stretch a rubber band, the rubber band has elastic energy stored inside it, ready to boom, bounce back, okay? So that energy can be calculated using the area under the graph, which is just a triangle. So half times the base times the height, half times F times X, okay? That is the area or the potential, elastic potential energy. There are also few things that affect the stiffness of a spring. First of all is the length. The longer the spring, now there's a mistake here, you help me correct this. The longer the spring, the weaker it is, okay? The longer the spring, the less stiff it is. Okay, shorter springs are stiffer. Yeah, longer springs go wong, 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 like that. Okay, all right. Next is a coil diameter. Coil diameter meaning this versus this. Okay, now the wider the coil diameter, the lower the spring constant. Means this is weak. The smaller diameter one is stronger. Okay, for this one, you just have to remember the slinky. You know the slinky spring, the big spring that can go, right? Okay, that spring is very, very wide diameter, and that is very, very not stiff. That's that slinky. Okay, the next one is the wire itself. Is the wire itself a thick wire or a thin wire? Meaning this versus this. Okay, the wire thickness itself. Of course, the thicker the wire, the more material there is, the stronger it becomes. Okay, so the greater, the thicker the wire, the stronger the spring, the stiffer the spring. And lastly, it's up to the material. If the material itself is hard, then the spring constant would also be higher. Okay, so it also depends on what material you use. Lastly, springs can be connected in series or parallel. If you connect springs in series, every spring is going to get the maximum W. Okay, every spring is going to get the maximum weight. Yeah, so when you calculate their extension, they are going to get the maximum extension as well. Okay, maximum weight, maximum extension. Yeah, they'll get everything fully felt by both. But in parallel, right, they will share. So they will share with each other, divide by 2. Therefore, their extension will also be divided by 2. Okay, because they share. If you've got 3 people, then you divide by 3. Understand? So that's how these springs work. Okay, any questions you want to ask about the spring before we go into the exercise? Any questions that you're curious about? Okay, if not, then let's go on to the question. So, yeah, question number 3, this is on page number 13. So I have diagram 11.1a and 11.1b showing the same spring suspended by 1 Newton and 3 Newton weight to study the elasticity of a spring. X1 and X2 are the extension of the spring produced. So you hang 1 Newton, you get this extension. You hang 3 Newtons, you get this extension. What is meant by elasticity? Elasticity is basically, can you go back or not? That's elastic. Okay, can you go back or not? It is the ability of an object to return to its original shape and size. Okay, the ability of an object to return to its original shape and size. Now, if you want to add one more, you can also say after any forces are removed. After any forces are removed. Okay, yeah, after you remove the forces. Okay, so again, another compare question. Based on the diagram A and B, compare the spring constant, the weight of load, and the extension. 3 things are, okay? Don't just write one answer. 3 things are. Okay, first, spring constant. How to know whether the spring constant, which one is bigger, which one is smaller? You see the spring they use. Same spring. Same spring means must be the same spring constant. Correct enough? Same material, same diameter, same thickness, same length, same spring constant. Okay? So the spring constant is the same in 11.1a and 11.1b. Okay? I'm just going to write it shorter lah, huh? Okay, exam the time you go and write the full sentence lah. The spring constant is the same in diagram 11.1a and 11.1b. Now, the weight of the load, 1 and 3 are. So, weight of load, A is lesser than B. Okay? The weight of the load, A is lesser than B. Okay, then the extension of the spring, same lah. A lesser than B lah. So extension of spring in A is smaller than in B. Or you can always say the other way around. B is greater than A. Okay. Right. So again, after compare must be what? After compare must be relate. Relate what then? Relate the weight and extension. Relate these 2 things. Okay. So again, you see, you want to choose A or B lah, huh? If I choose A, I will say smaller weight, smaller extension. If I choose B, I will say greater weight, greater extension. Correct or not? Because in B, both are greater. Okay, so it's up to you, right? The greater the weight, the greater the weight of load, the greater the extension of a spring. Oops. The greater the weight of the load, the greater the extension of the spring. Okay? Right. They also ask you to name the physics law, by the way. Okay, but in spring, there are no other physics law. There's only Hooke's law only. In spring, there's only one law, Hooke's law. Hooke apostrophe S law. Okay, cool. Right. Diagram 11.2 shows a graph of force F against spring extension X for spring J. So this is the Fx graph. Based on the graph, explain how the stiffness of the spring and the elastic potential energy stored in the spring can be determined. They are just asking you to explain. If you were given this graph, how do you find the stiffness and how do you find the elastic energy? Okay, so first I will tell them, because F is equals to Kx, okay, and K is equals to F over X, that means Y-axis over X-axis, which also is the gradient, right? So I will tell them the spring constant is the gradient, okay? So you say the spring constant is the gradient of the graph. Okay, the spring constant is the gradient of the graph. Right? And then if I want to calculate the energy, energy is half Fx, which is like half of the base times the height, which is just the triangle under the graph. Okay, so I tell them the elastic potential energy, is the area under the graph. Okay, elastic potential energy is the area under the graph. Right? Yeah, make sense, huh? Anyone not done yet? Anyone need a bit more time to copy? All good? All done? All right, let's go on to the next part. So here I have a swing sitting by a child, set by a child. The spring of the swing is extended when the child is seated. Okay, you're required to create a swing that can be used by adult of larger mass. Okay, so you see, you are creating the swing, not just the spring only. Okay, state and explain your suggestions based on the characteristic of the cradle and the spring. So don't focus all your answer on the spring only, even though you know this is a spring question. Okay, I don't want 5 answers just for spring only. Yeah, you have to mention what can you do to the cradle, what can you do to the swing itself also. Okay, so let's start by talking about the spring. Never mind. Okay, let's start by talking about the spring first. So if I want the spring that can hold the adult, that means my spring must be stiffer. Okay, so to get my spring stiffer, what are the things that I can do? So for example, I can use a thicker wire, yeah, thicker wire of the spring. Okay, why? Because the thicker wire of a spring can make the spring stiffer. Okay, can make the spring stiffer. Okay, what else can I do? The coil diameter. Yeah, we know that the coil diameter needs to be smaller to be stiffer. Or you can say the length should be shorter right? Shorter spring will be stiffer. It's up to you. Okay, so many things you can write. So let's say shorter spring. Okay, shorter spring because it has a higher spring constant. Okay, now although these two, right, they actually mean exactly the same thing, but I write it in two different ways so that it doesn't look that boring. Of course, you can put the same reason. Yeah, you can say stiffer, but it will look a bit boring, lor. It will look, the teacher will feel like you got no other answers already. That's all you know how to say only. So you try to write it in another way. So these two actually exactly the same meaning one. High spring constant means stiffer, but I write it in another way. So not so boring, no? Okay. Besides all the characteristics that we talked about just now, like shorter, bigger coil, use different material, okay? There's another thing that we can do, which is you can put few springs in parallel, correct or not? Right? You can use multiple springs in parallel. Use multiple springs in parallel, just like, like in the baby cot, you can have multiple springs also. Use multiple springs in parallel. Okay, so that your extension of the spring won't be so much. Okay, smaller spring extension. Because now they share already, ma. They share the load already. So their extension won't be so much. Smaller spring extension. Okay, next. Okay, now I think enough of the spring already. Let's talk about the swing itself, the cradle itself. Okay, so what can we do to the swing? They already label the different parts of you. Means they expect you, right? Say something about the nest, say something about the base, say something about the pole, the tiang. Okay, so let's say the nest. You want to fit an adult, so you need a bigger nest. Okay, bigger nest so that can fit a bigger adult. Okay, can fit bigger adult. And then what about the base? If we want it to be more stable, then we should get the base, to be wider base. Okay, so that it is more stable. Okay, more stable. Okay, all right. Now, I'm going to skip question number 4 because it's also about spring. I believe you should be able to do question number 4. Nothing too hard about this question. Okay, it's also about spring only. So you see, same thing lah. You have to talk about the different parts of the pogo stick and all that lah. Okay, so we're going to go to question number 5 because I want to talk about the lift question. Okay, you go to question number 5. This is page number 18. Okay. You have a boy standing on a weighing scale in a lift that is moving upwards with a uniform velocity. So this is in diagram 2.1. And then we have another boy, same boy in a lift that is accelerating downwards in 2.2. In diagram 2.1, label and name the forces acting on the boy. Okay. So you have to label all the forces. Actually, not a lot, only 2. Okay. One of it, like I said, always exists one. There is a force that always exists on us. It is our weight. Okay. Now, the 50 kg is there to distract you only. That is not your weight. 50 kg is your mass only. Don't care about the arrow. Okay, don't care about the 50 kg. That's your mass. You still need to get the weight. Different. Weight is a force. Okay. If you have a force going down, you must have a force going up. Okay. And this upwards force is called the reaction force. Because if you are pushing down on the floor must be pushing you back up. Okay, we call that the normal reaction force or just reaction force. Okay. Now, state the relationship between the forces in A1. So you look at this, right? To answer the question of this, you must first understand what is uniform velocity first. Okay. So uniform velocity means your speed doesn't change, right? There's no acceleration. Okay, your speed just maintains the same. So if there is no acceleration, right, in uniform velocity, it also means that your net force is 0. Okay, and if your net force is 0, what does that say about your forces? They must be balanced. Okay, net force 0 means your forces must be balanced. Left must equals to right. Up must equals to down. Weight must equals to reaction force. Okay, that's the relationship. Weight is equals to reaction force. Okay, get it? Now, what is the reading of the weighing scale in diagram 2.2? Okay, let's look at how to solve a lift problem. Super easy. If you really pay attention once, you will never have to do any revision for lift because you will be able to solve any lift problem. Okay. Now, first of all, in 2.2, right, there is a force going down and it's called weight. There is a force going up and it's called reaction. Okay, so these are the two forces up and down, right? We know that in 2.2, there is an acceleration. So if there's an acceleration, I could say F must be equals to ma. None of it is 0, right? There is an acceleration. F is equals to ma. Okay, so the thing is this F. This F is resultant force. And how do you get the resultant force? For example, if let's say I have an object, there's 2 newtons pulling here and there's 5 newtons pulling here. How would you get the resultant force? You will take 5 minus 2. Yeah, you minus it and then you will get a resultant force of 3 newtons like this. 5 minus 2 ma. Okay. So here also the same thing. How you get the resultant force is you take the 2 forces you minus. Reaction minus weight or weight minus reaction is possible. This is entirely up to you. You want reaction minus weight or weight minus reaction. You own self set whether you want up to be positive or down to be positive. The other one will be negative. Okay. Now, usually what I do is I follow the direction of the moving. Okay. If this thing is moving down, then I will let down become positive. Not fixed one. I depend on where is it going one. So this is moving down, so then down is positive, up is negative. If this is moving up, then I will set up is positive, down is negative. Okay, this means positive, this means negative. Okay, now, yeah. So if now down is positive, right, means weight minus reaction. Okay, and not the other way around. So I'll go with weight minus reaction equals to ma. That's my resultant force. Okay. Now, why I always choose follow the direction of movement, right? Because usually I want my acceleration to be positive. Right now, my acceleration going down, so it's positive. I don't need to worry about this one. Yeah, I just put in the number only. Okay. So weight minus reaction. You know how to get the weight, right? Okay. The weight must always be equals to mg. Okay, so you know how to get the weight, mg minus r equals to ma. Okay. Now, by the way, do you know what you're trying to find or not? Do you know what you're trying to find? The reading of the weighing scale. Reading of the weighing scale is actually R, in case you don't know. Yeah. Reading is actually the reaction. Because the weighing scale is not supposed to tell you your weight. The weighing scale not telling you the weight. The weighing scale is telling you how hard does he need to push you back up. Okay? He's telling you how much force he is using to push you back up, not how much force you are pushing down with. Okay? So the weighing scale tells you reaction instead of the weight. Yeah? Okay, so mg, the mass is given 50 kilogram. The g is always 9.81. R is what we're trying to find, equals to the mass 50 times the acceleration of the leaf 2. Okay? The acceleration of the leaf is 2. So can you get R for me or not? Can you get R for me? How much is the R? 390.5. Is it? Yeah? 390.5 newtons, because it's a force, the reaction force. Okay, what is his actual weight? What is his actual weight? His actual weight is what? 50 times 9.81. 5, 4, 4, 5, 4, 9, 490.5. Is it? 50 times 9.81, 490.5 newtons. Okay, all right, that is his actual weight. But the weighing scale is showing lesser than that. The weighing scale is showing 390.5 only. Does that make sense or not? It makes sense. Because when the leaf go down, right, you will start to sort of like you start to like float up. Right or not? Okay? You know, like in movies when the plane, let's say someone hijack the plane, then the plane start to dive down. Then inside the things will start to rise up, start to float up, because they become lighter. Okay, they become lighter. Yeah. So actually, when you move down, okay, you will sort of like, I mean, you will move down together, correct? Yes. But then you will like float up a little bit. So it will make you a little bit lighter, okay, than what you actually are. That's why it shows you a smaller number. Okay. And what if the leaf accelerate upwards suddenly? This is if the leaf accelerate downwards, But if the leaf accelerate upwards, then it will become what? It's like you sit in a rocket and then the rocket fly up, or you sit in the plane and then the plane fly up suddenly. Then you suddenly become like that. Suddenly get pressed down. Right now, you get pressed down on your seat because you become heavier. Okay, so the weighing scale will show you becoming heavier. Okay, so the scale reading will increase. Okay, the scale's reading will increase. Okay, Why the scales reading will increase? Very easy. You just tell them, what is the scale reading? The scale reading is R ma. Because the reaction force, the R increase. That's why the scale reading increased lah. Okay, you say the reaction force, which is R, will increase. That's why the scale reading will increase. Okay. Right. Now, what is the change in the weighing scales reading in diagram 2.1 if the cable of the lift suddenly snap? Okay. If let's say this lift, the cable suddenly pop, snap already, the lift will start to drop down. Correct or not? Okay, you see, if this thing is going down, you will feel lighter. So if let's say it snaps and this thing goes down, you will feel lighter. But right, how light? Okay, how light will you feel? Now, when you drop down, right, it's like, again, the plane go on free fall. Okay, if the plane go on free fall, then you will start to float inside the plane, ma. Correct or not? Okay, you'll float inside the plane. So that is because you now feel weightlessness. No weight, zero weight. Okay, when the plane suddenly drop down. Okay, so same case here. Yeah. Normally, if the lift slowly move down, you just feel a bit lighter only, but you still got weight. But if the lift fall down with you, the lift just drop down together with you, you will actually feel zero weight. You know why? Because what is the lift acceleration if the lift just, the wire snap and then the lift just fall down? What's going to be the acceleration of the lift? What do you think? If the lift just drop down like that, start falling, nothing stopping it, the acceleration of the lift going to be 9.81. Correct or not? Yeah, anything free fall, right? The acceleration is going to be 9.81. So can you imagine this acceleration 9.81? You try to put it inside here. This acceleration of the lift, you try to put 9.81. 50 times 9.81 minus R equals 50 times 9.81. So this thing, this R going to be 0. If you move this around, you calculate the R, is going to be 0. Okay? So the weighing scale reading, right, will actually be 0 if you suddenly just, if the lift just goes on free fall. Okay? So you say the weighing scale reads 0 newtons. Okay? The weighing scale reads 0 newtons. All right, understand? Okay, now last question, question number 6. So here I have a caravan. Caravan is basically this thing lah, right? The caravan of a mass 12,000 kg being towed by a car with a constant thrust of 3,000 newtons. The force acting upon the caravan are in equilibrium. What is the meaning of forces in equilibrium? Just now we already wrote already lah. Okay, so you know how to answer this question already. It just means there are no resultant forces, or there's no net force on the object acting on the object. Okay. On diagram 3.1, label the two forces acting on the caravan. Okay, so what are the forces acting on the caravan? Now, thrust is basically the engine force, right? The engine force of the car is pulling this caravan forward. So the pulling forward force is 3,000 newtons. Now, of course, you should label it as thrust lah. not 3,000 lah. Okay, you should label it as thrust. And then if there is a forward force, there has to be a backwards force. And what's the backwards force going to be? It will always be friction. Okay, for a moving object, the backwards force is always friction. Okay, that's the labeling done. Okay, the caravan is moving with a constant velocity of 5 meters per second. What is the magnitude of frictional force that is acting on the caravan? Okay, constant velocity. Again, constant velocity means what? Constant velocity means acceleration 0. Okay? Acceleration 0, which means force 0, which means no net force. Okay? Which means everything is balanced. Up is equals to down. Left is equals to right. Thrust is equals to friction. So the friction is 3,000 newtons. Okay, 3,000 newtons. All right, so sketch a velocity time graph of the caravan's motion. Okay, now this is supposed to be more of your junior's exam paper lah. This one, but never mind, you need to know this also. Okay, so velocity time, units for velocity is meter per second, units for time is seconds, okay? So how do we draw constant velocity? Constant velocity means the velocity always remain at 5, 5, 5, 5. Like that, ma. Every second also 5, ma. Okay? So it's just one horizontal line at 5. Okay? The thrust acting upon the caravan is increased to 4,000 newtons, meaning the pulling force, the forward pulling force is now 4,000 newtons. But at that moment, at the moment when you just have your pulling force, right, increase to 4,000, the friction still remains the same. The friction is still 3,000 newtons. So what is the resultant force now? The resultant force will be my thrust minus the friction. There is now a result. It is no longer balanced. So your resultant force is 1,000 newtons. Okay? And can we use that to calculate the acceleration of the caravan? We can. We know that F is equals to ma. This force is the resultant force, which is what you've just calculated. Okay? 1,000 equals to the mass of the caravan, 12,000 kg, times A. Can you get A for me? The acceleration. What is the acceleration? (0.083). Okay. 0.083 meter per second square. Yeah, because it's an acceleration. Okay, meter per second square. All right. Now that is the last question already. Okay, of course, we didn't do the question number 4, but I believe you can just try that on your own. Okay, now I just want to take a few minutes and talk about the inclined plane, just in case, right? Remember just now the one I said I was going to talk about it. Okay, so for inclined plane, right, actually it's the same as what we've been doing, taking one force and splitting it into two. Okay, like this force here, we can split it into horizontal and vertical. The inclined plane is the same. Okay, so inclined plane, right? It'll be like this, and then like this. Okay, and then what they'll do is they'll put an object here. Okay, this object is gonna have a weight. Yeah, the object is gonna have a weight, and this weight is equals to mg. Don't forget. Now the weight can be split into two portions. It can split into one that follows the slope and the other that is 90 degrees to it. So the one that follows the slope, we call it the parallel component. The one that is 90 degrees to it, we call it the perpendicular component. Okay? So your job is to take these three forces and form a triangle. Again, just take three different pen or pencil, point them in these three directions, just put them on top here, and then start to move them around. Move, do not rotate. Okay, just move wherever you want to move it. Okay, so you'll realize that if, let's say, you move your parallel down, you get a right angle triangle here. Can. Okay, you can move your perpendicular over here, you get a right angle triangle. Can. No problem. Okay, so choose whichever one you want to move. Yeah, and then this angle, the angle of the slope, will always be between the weight and the perpendicular. If, let's say, you move the parallel down here, the angle will be here between the weight and the perpendicular. If, let's say, you move your perpendicular over here, right, then the angle will be here between the weight and the perpendicular. Okay, no matter what, always between the weight and perpendicular. This only applies for slope, for inclined plane, which is a slope. All right, so once you got the triangle ready, once you got the angle ready, all you have to do is your so and ka, sometimes toa. Okay, just do your so, ka, and you'll be able to get how much is the parallel, how much is the perpendicular. That's all you have to do. Okay, understand? All right, any questions or not for this? Any questions for today's class? Okay, all good, everyone also good? Yeah? Okay, if there are no questions, then we will call it a day for today. Thank you for coming to class on a Sunday, okay? And good luck for your next exam, all right? So I'll see you again soon, okay? Bye-bye.